This is the symbol.
Is this classified as a speaker? I'm just asking because I'm
Speaking event?
Yes.
So make sure you sign in on the sheet, put your faculty number or your there.
I'm good. I just didn't want to come in and then
No, that was good. It was a straight diagram. I wrote on the whiteboard. I said, I don't like doing the letters. You know what I mean?
Hey folks, just since some of you weren't here when I mentioned this before, please make sure that you put plastic especially in that box, okay? So I will take it and recycle it. Please do this. All right, we'll get going in just a couple minutes. We're just waiting on Dr. Pesley right now. So he should be here real soon. But if he's not here in time, we'll just get going at 1:20 promptly because I know some of you have other classes. And if you don't get more people, you can eat more pizza.
That's what I'm waiting for. Close the door. This is my lunch. What?
Okay, as you come in, we're going to get going. So again, please sign in if you're getting credit for some reason or another for this class, which probably most of you are because we're bribing you. Make sure you clearly, neatly print your faculty member or the program next to your name. All right, I've been making photocopies of these sheets and distributing to faculty members. If you know for sure you didn't do that the first day, send me an email, please, so that I can take care of it. All right? There's pizza in the back. It looks like we're not going to have as big of a crowd this last time, or at least not right away, so you can help yourself to a second slice if you got cut off. Please put your recycling, especially your plastic, in the back. With that, I'm going to start out with our physics professor, Mr. Dan Ford. Dan did his graduate degree at Clemson, and he's going to be talking to you about the physics of the greenhouse effect.
Hello? Can everyone hear me? Yeah. Awesome. All right, so just to get a couple of things out of the way right up front, we are, the four of us, or three of us at the moment, are going to be going back to back. While I would love nothing more than to answer your questions as they come up, we're trying to keep everything kind of short to get to those questions. So if you have a question while any of us is speaking, please write it down. Save it for a little bit later. The goal of this is to be able to answer your questions. But we do have to delay a little bit to get all the information out first, because there's always a chance we're going to answer it. And if we stop for every question along the way, we're going to run out of time. So any questions that you got, Just hold on to them for a little bit. We're going to go as quickly as we can, all right? So, what I'm going to be talking about is the greenhouse effect. And the greenhouse effect is the sort of physical reason behind global warming or climate change. And this is basically how it works. So, we start out here. Sunlight reaches the earth and warms it. I'm sure all of you have felt a warm sunny day before, I hope. So, sunlight reaches the earth and warms it. A little bit of that sunlight heats the atmosphere, but most of it makes it to the earth. So, because the earth is warm, it's going to radiate some of that heat. If any of you have ever had to walk barefoot across asphalt, I'm sure you have experienced this. So, as the earth is warm, it's going to re-radiate a lot of that energy. And there's where part of our problem is, because if you notice, very little of that energy actually makes it back out to space. Most of that energy gets stuck in the atmosphere. And that means that the atmosphere has a lot of energy. Now, it's not going to hold on to it perpetually. It will also radiate the energy. And as you can see, some of that energy doesn't make it back out to space, but most of that energy gets stuck radiating back down to Earth, which then warms it, which means we have more energy for the Earth to re-radiate, which gets stuck mostly in the atmosphere, which mostly comes back down to Earth. You see this cycle we're talking about? That is the greenhouse effect. And this is not really something that has ever really been up for debate. This has been demonstrated time and time again. We have greenhouses, that's what it's named after. We see this effect. But there are still a couple of things that aren't obvious about this. So, why does the Earth actually radiate heat? So the reason why the Earth radiates heat is the same reason you can see him in a thermal camera. Literally everything will radiate at least a little bit. Now, we obviously don't radiate light, no matter how bright you are, but we do radiate in a certain way. So, everything that isn't absolute zero, which is everything, will radiate at least a little bit. And there's a couple of things I'm going to point out, because I'm going to reference it later. There's a little bit of a glow around his hand. That's going to be a little bit important. And his glasses. So keep that in mind. I'll be flipping back and forth. All right. So the Earth radiates because everything radiates in some way. We just don't radiate light. So here's sort of the ultimate question I see most frequently. Why can't the heat just leave? It made it in just fine. Why can't it leave? And the reason for that is transparency. So, different things are transparent in different ways. Our big black plastic bag here is not transparent to light. You cannot see his hand with light. But you can totally see his hand if you're looking in the infrared spectrum. That bag is transparent to the infrared spectrum. It's not transparent to light. In the infrared spectrum, you can't see through his glasses. They don't allow heat to pass through, but you can see through his glasses with light. Kind of make sense? So, different things are transparent in different ways. My last example. We are in a closed room. There's not really any windows here. It's impossible for you to see the nearest cell tower. But I'm willing to put money on the fact that all of you still have cell signal, right? Different things are transparent to different frequencies. Our atmosphere is transparent to visible light, and a little bit of radio waves, and basically nothing else. Our atmosphere is basically opaque to heat. Heat cannot propagate through it very well. So, the thing that makes our atmosphere opaque to heat is just the fact that it's made up of gas. Literally any atmosphere, every atmosphere, will trap heat to some extent. We can see this on every planet that has an atmosphere. Venus, even Mars, Jupiter, literally all of the planets that have atmospheres exhibit a little bit of the greenhouse effect. The thing that exacerbates it, the thing that compounds, are something called greenhouse gases. Any gas can trap heat a little bit. Greenhouse gases are really good at it. Really good at it. And they tend to be our more complicated gases. Nitrogen is an element. You can see it over there on the periodic table, or over there, if that's easy for you. Nitrogen is an element. Oxygen is an element. They are relatively simple. Water vapor is a compound. It's a little bit more complicated. Carbon dioxide is a compound. It's a little bit more complicated. They hold heat better, and they are better at trapping heat. I can give you one fairly simple example of this. On a very, very, very cold winter's day where it's sunny outside, it can be bone-chillingly cold. And I'm sure that many of you have experienced this. But if it's winter and you have a little bit of cloud cover, frequently, not always, but frequently, it's going to be a little bit warmer than those nice, clear days. Clouds are made of water vapor. It helps trap the heat near the surface. So, that is pretty much everything for me. Up next is Dr. Mary Powers.
So part of what Dr. Fork was talking about is something that I'm going to add to. So I'm going to go past some of what he said because I want to get to a couple of other things that go along with the greenhouse effect and talk a little bit more about the climate. So Earth's climate, there's like 3 major factors that affect it. And these aren't all, these are just some of the major factors. Solar radiation, what he was talking about, the sun coming in, that affects our climate. How hot or cold it is affects the winds and the currents. And so the wind's another thing that affects our climate, as well as ocean currents. And what people don't think about ocean currents having an effect. Okay? But these are some of the 3 major factors that affect the climate. Before we go on, let's get some definitions straight too. The global climate change, what is that? It's a long-term change. We're talking about long-term in the Earth's climate, okay? Or the region of Earth. So it's a long-term process. That's the climate change. Then we have something called weather, and we also have climate. What is the difference? Weather is what you really get on a very short time period, right? It's what happens. Oh, there's the weather. Oh no, we got weather coming. You know. Climate is what you expect to get. Okay, and it's a very long period of time that we're looking over. Okay, so our climate during the winter is usually colder than it is in the summer, or we can think about climate over decades also. So a longer period of time. And global warming, which we're interested in, is the increase of the Earth's temperature. So it's the Earth's surface increasing, okay? And why it's increasing so much is these greenhouse gases, okay? He's already talked about the energy balance for the Earth, okay? Which is one of the things that we have to think about when we're talking about this, either global warming or the climate change and all this. And we want to balance the amount of incoming radiation versus outgoing radiation. So it's the same thing that you just said. And the bottom line, I'm just going to kind of go past this because the bottom line is that a lot of the radiation that comes from the sun gets trapped into the atmosphere. You know, 60, 70%, 60, I think it's 67%. A lot of energy gets trapped in the atmosphere. And that's what makes it so nice and toasty here on Earth. That's why Earth is so wonderful, because we have this atmosphere that gives us this little greenhouse effect and keeps us nice and toasty, okay? Which is fine. But there's always an issue with this greenhouse effect, right? So it's a natural process, okay, that keeps us nice and warm. And that's what, all right. So major greenhouse gases, he talked about those too. Carbon dioxide, I excluded water. Water vapor is probably the best greenhouse gas, but it's all over the place and we can't really control that. So it's something that we don't really talk about. But carbon dioxide and methane are 2 gases that are really crucial. We'll talk a little bit about carbon dioxide and methane in a minute. There's also nitrous oxide. That's produced from like catalytic converters and some other things. CFCs are wonderful little molecules that are not reactive. They were made to help with refrigeration, and it turns out that they made ozone holes, and they're also very good greenhouse gases. They absorb a lot of energy and trap it. Same thing with the HCFCs, same thing. Sulfur hexafluoride's another one. All of these things trap heat very, very, very well, and then re-radiate it out, okay? So why do we focus, there's all these other gases, why do we focus on CO2? Why do we focus on carbon dioxide? Because as humans, we release a lot of CO2 globally. It's a lot in our atmosphere. Look at this increase. Since 1750, which is before we had too much industry going on here, it was 280 parts per million. Now it's up to 407. That was just as of a month ago. Okay, so 45% increase from them. So it's a lot, you know. So that increases that greenhouse effect. Okay, when he was talking about that cycle that we see, so it just gets it warmer and warmer and warmer. And that's an issue. Okay? So it stays up in the atmosphere for a very long time, the CO2 does, and it absorbs into the oceans. A lot of what we produce is absorbing into the oceans. Okay, so the ocean's going to take care of some of it for us. So let's talk about methane. Methane gas, a little bit CH4, it's actually better at absorbing infrared heat than CO2 is. And so it has a potential to really create havoc with the greenhouse effect. However, there's not as much in the atmosphere. Okay? There's 50 times more CO2. So methane, you can get it out of the atmosphere really quick. And it's also in the oceans as what we call a methane hydrate. The water molecules make a little cage, and that methane is sitting in there. And they're all just kind of settling on the bottom of the ocean. They're not really doing anything. So we have methane there. We actually have methane in our permafrost in the north and in wetlands too. And so as long as it stays reasonably comfy here on Earth, we don't really have a problem. So we need to talk, the oceans have a lot to do with this, and people don't talk too much about the oceans. But the oceans, they cover a lot of the Earth, right? And they are one of the major climate and global warming drivers. Okay, one of the functions of the ocean is to transfer your heat from the tropics up to the latitudes, but it's very, very slow. So all the stuff that happens in the ocean is very slow. So that's why we're not seeing a lot of fast changes. Okay, it takes a long time to get these changes to go, but it absorbs a lot of heat because it's water. Okay? It also absorbs a lot of CO2. The carbon dioxide in the oceans, what it does is it reacts with the water and it forms carbonic acid. So what do you think happens to the oceans? They start becoming acidic. Okay? Life doesn't like that very much. Okay? Other organisms, so marine ecosystems, they haven't seen too much yet. I think they're starting to see it. Okay? Again, it's a slow process. So far, only 40% of what we produced has been absorbed. CO2 has been absorbed by the oceans. About 80% is all it can do. So once it reaches that capacity, then the CO2 stays in the atmosphere. Okay? You'll get more and more and more CO2 released once the oceans start to warm. Why? Because it's a gas dissolved in water, and if water starts to bubble, those are the gases that come out. So the gas is going to come out as Earth heats. It's going to heat up the water, right? Okay? And as that happens, the CO2 comes out, and those little methane hydrates will also decompose. The methane will come out. Methane's a much better greenhouse gas than CO2, so we're going to get more of that in the atmosphere. Both greenhouse gases will lead to more global warming. That's not good. And currently, up in the north, the permafrost is already melting. So some methane's already being released, and the more it thaws, the more methane comes up, the worse things get. And that's a real concern, okay? So if I put this up, here are my references, because you have to have references when you do scientific work. So make sure that you look at some of these things, and we'll post this, okay? All right, next up. Who's next up? Okay.
Heavy pizza. That's not global. Well, that's kind of a global warming thing, right? Anyway, enough of that. I presented these slides last Wednesday, with a small kind of disappointment. I had added to the set some URLs that we could pick up some things to share. And for some reason, the way the displays all came up, they came up behind the PowerPoint. We couldn't figure out how to bring it back to forward and so forth, at least in the time we had. So I'm going to try that. All I really want to show is, from this set, is a few key slides, just to reinforce some of the things we've said here, and then go to the solution, okay? I think they made a very, very good case that the idea of the global warming is entirely true. One of these slides, some of the experts that I have on here who come from a variety of climatologists, volcanologists, geologists, and so we're very well-known, peer-reviewed, published scientists who have been there, gotten the first source information, and published on it, okay? And that's what I rely on, you know. If you want to get into a discussion about whether this science is true or that aspect is false or whatever, okay, the only real measure that we have is the peer-reviewed journals, and that's been going on for years. One of those came from a fellow named Joseph Fourier. Any of you mathematicians in the group would know Fourier's a Fourier series, and the man who gave us the technology behind the math, if you will, behind heat transfer. And he's one of the very first ones who talked about 1820. He talked about climate change, the probabilities. And then a fellow named 1890, Svan Arrhenius, who the chemist would know, among us would know, as Mr. Acids and Bases, right, in solutions. That was his big thing. But he wrote on it, and he conjectured what would happen if we lost all the CO2. We said, what the heck? I mean, 280 parts per million, that's not a whole lot of CO2, big deal, right? But you have to put that in perspective. For tens of thousands, hundreds of thousands of years, actually, roughly that level of CO2 sustained all of the foliage on the Earth. It's enough to keep all of the plants alive, okay, and growing. So is it insignificant? My gosh, no, right? But at the same time, they made the case that it also traps heat. Its absorption wavelengths are such that it will absorb the infrared wavelengths coming from the Earth. So there's no question. The science is unquestionable at this point. Okay. So let's see if I can find here. I'm going to try to do it this way. I'm just going to buzz down through here. But you can see that up there. There's a partial reference of people with evidence of climate change who've written about it, peer reviewed and so forth. Organizations, some of these are those who went to Greenland, went to Antarctica, did the ice cores, from which we know what the atmosphere concentrations were, going back over literally, I think now they go back to as much as 800,000 years. Okay, so we've known for a long term exactly what the atmospheric contents have been. Okay, down the bottom of this, let's see. Well, there's the IPCC, which is in so much controversy. We'll come back to that. Okay. In fact, it is people like this who contributed to getting that book written, but it's probably the most maligned among the so-called naysayers, if you will. So let's go down here to, I'm going to brush over, hopefully some of you saw these slides last week, but I want to get to one that has a URL in it, and hopefully this one works. Let's see, do I want to do that one or not? We did the tour of the glaciers. I presented a series of, I don't know, what was it, 10 or 12 glaciers who have 70 to 80% have melted not only within the last 100 years, which is totally unprecedented, but some of them have occurred within the last 20 to 40 years. Okay, and I actually have visible evidence of that myself, having seen Glacier National Park, Grinnell Glacier, okay, here's my age coming. You ready? 1961. Okay, the age of your granddads. Anyway, but I saw it. And in 2005, I happened to see an aerial photo of the whole glacier. There's 150 glaciers out there that used to be, and 70 to 80% of them were simply gone. Okay, it was snow-capped mountains where glaciers used to be. All right, so let's go a little bit further here. I'm going to buzz through these. Quick. Have most of you here Wednesday? Was anybody here who was not here Wednesday? Okay, just a few. Let me go kind of slowly. I don't want to take too much time with this, but these are before and after pictures going anywhere from the 1800s to present to as much as the 1990s, if you will. Or in my case, it was the 1960s to present. And here you can see, this is past year's glacier in Australia.